Okay. Let's continue. And the next talk this session will be by Vikraman from Indian Institute of Technology and Press. And the name of the talk is Equivariant K Theory of Finger Prime.
So, first of all, I would like to thank the organizers, Professor Mikia Masuda and Shintaro, for this invitation and for giving me this wonderful opportunity. I feel very happy to be again part of the toric topology conference. So today I will speak about the equivariant K-theory of Springer varieties. So we will start with the definitions of the Springer variety of type A. So, we had given some of these definitions during the informal seminar. So we will again start with the basic definitions. So Cn denotes the n-dimensional complex vector space for us. And so we denote by F or FCn this full flag, the variety of full flags in this Cn. So dimension of Vi is I. And we fix one nilpotent linear transformation of Cn, so, or a nilpotent matrix. We fix a nilpotent matrix. And by F sub n, we denote the following subvariety of this full flag variety. So we take those flags which are left stable under the nilpotent operator, but because this is nilpotent, it will take it to Vi minus 1 for 1 less than or equal to I less than or equal to n. So this is called as the Springer variety of type A associated to n. So we are doing everything in type A here. So this is the usual flag variety, and this is known as the Springer variety of type A associated to the nilpotent operator. So the moment we have a nilpotent matrix, we have the Jordan canonical form for it. And therefore, we can take the sizes of the Jordan block, and they are the decreasing sizes. So there are L Jordan blocks, and these numbers denote the sizes of the Jordan blocks. And because of that, this lambda, which denotes this lambda 1 up to lambda L, this gives a partition of n. And this is associated to the nilpotent operator. By general theory, it is known that the Springer variety associated to n will be isomorphic to F sub. If you conjugate it by some invertible matrix, these two varieties are isomorphic as algebraic varieties. So this is generally known. So it is independent of in the conjugacy class. So we can assume that n itself is in the Jordan canonical form from now for simplicity. So we will give the two basic examples of the Springer variety. So we first choose that all the Jordan blocks are of size 1. So in this case, L is equal to n, and we know that the matrix n is just the zero matrix. So in this case, there is no condition imposed, so it is the full flag variety. On the other extreme, when lambda has there is a single Jordan block, then a nilpotent operator has a single Jordan block. This is known as regular nilpotent because it has a single Jordan block. So it was also discussed in many of the other talks. So today also it was discussed. So in that case, it can be seen by checking by some linear algebra argument. If it fixes the flag, then it must be just consist of the single flag, which is the standard flag given by this the basis, the standard basis vector of Cn. So it can be seen that it consists of just one single point. So we can now fix some torus. This is the compact torus consisting of these diagonal matrices in GL and C. So TAs are C, and we are taking that they are in S1 from 1 less than or equal to I less than or equal to N. So there is a natural action of this torus on the full flag variety because by restricting the action of GLN, because we know that it fixes the dimensions, but we cannot extend this. We cannot say that Tn will act on F lambda because there we have imposed some conditions given by the nilpotent operator. So we need to find the correct torus which acts on this F lambda. So for that we choose an L dimensional torus where L is the number of Jordan blocks. So we choose this torus consisting of scalar matrices. So these are I lambda 1, I lambda 2, I lambda n are the identity matrices of sizes lambda 1 cross lambda 2. So lambda 1, lambda 2 cross lambda 2, etc. Lambda L cross lambda L, and HIs are arbitrary scalars, so which are coming from S1. So this is a torus which is isomorphic to S1 power L. And we can see that because TL commutes with the nilpotent operator, that TL will act on the Springer variety. So we now recall some known things about the Springer variety, the history of this. So as the name suggests, this was studied by T.A. Springer and by a series of papers by Springer and Hota Springer, which appeared in 1976, 77, 78. So what Springer showed was there exists the action of the symmetric group Sn on the cohomology of this Springer variety, so with complex coefficients. And so he also found this determined that this cohomology ring can be realized as isomorphic as an Sn representation to this induced module. So if we take this trivial representation, so these are the product of the symmetric groups corresponding to lambda 1 up to lambda L, and we take the induced representation of the trivial representation. This is denoted by M lambda, and this will be isomorphic to H star of F lambda C as an Sn representation. So this is what was shown, and it's also compatible. So we will come to this soon, that because there is an Sn action naturally on the cohomology, so this action what we are giving will be compatible with the action on the cohomology of the full flag variety. So the other important results in this order is that Spaltenstein gave an algebraic cellular decomposition. So that means there is a cellular decomposition where the cells look like affine spaces. There is a algebraic cell structure with exactly these number of cells, where n factorial by lambda 1 factorial, etc., lambda L factorial. And these also are, there is one cell for every fixed point. So these are exactly the number of fixed points in the Springer variety. Other than this, De Concini and Procesi in 1981, they described this cohomology ring of the Springer variety in a geometric way by the coordinate ring of some maybe non-reduced scheme, non-reduced variety. So TC denotes the Lie algebra of this torus, and this is we take n inside MNC, the nilpotent operator inside MNC, and we take the adjoint action of GLN on MNC, and we just take the closure of this orbit of GLN, of the orbit containing n, of the closure of the orbit of n inside MNC. So that is not of where n now is the Jordan form associated to the dual. We can also take the dual um, this vector, this dual to the partition. So for that, there will be an important operator, and this is the closure of the orbit of n in MNC under the adjoint action intersected with these. So this we are not directly using, but we need to mention that there are these results. And Tanisaki has described the cohomology ring with complex coefficients of the Springer variety as a quotient of polynomial ring in n variables over C by an ideal of relations. They are known as Tanisaki ideal. And whatever Tanisaki described with complex coefficients, it can also be shown for cohomology with integral coefficients. He has done it for the results follow also for cohomology of the Springer variety with integral coefficients that we can describe with the same ideal, because the ideal contains only integral coefficients. So the same description holds for the integral cohomology ring of the Springer variety. More recently, Abe and Horiguchi in 2016, they gave a description of, so we have seen that there is an action of the TL on the Springer variety. So it's natural to ask the TL equivariant cohomology ring of the Springer variety with integer coefficients. So they describe they gave a presentation for the cohomology ring or the TL equivariant cohomology ring of the Springer variety. So which we know is described more generally using this associated construction, the cohomology ring of this with integer coefficients. So with this is the classifying space of the principal bundle. So this is known as the TL equivariant cohomology ring of the Springer variety. And so more precisely, they gave a presentation for this as quotient of a polynomial algebra over this H star of BTL Z. So this is the cohomology ring of the classifying space, which is well understood. So modulo the equivariant, the ideal of relations is an equivariant analog of Tanisaki's ideal. So we will fix up some more notations before we first state Abe Horiguchi's theorem. So you consider the inclusion iota of the Springer variety inside the full flag variety. So on the full flag variety, we know that there are the tautological line bundles, namely the fiber over any flag for this line bundle is given by the quotient of these vector subspaces. So where Vi minus 1 Vi, they are the subspaces here in the flag. So the fiber is Vi mod Vi minus 1. So these are called tautological line bundles on F. So we also know that because there is a natural Tn action on F, and these are Tn equivariant line bundles. So that is again important for us that this respects the Tn action. So we will give the more detailed definition of TL equivariant vector bundles soon, but these are TL equivariant line bundles. So there is a Tn action on these line bundles. So now we can consider the restriction of these line bundles on the Springer variety or the pullback by this inclusion map. These are known as the restrictions for 1 up to n. So they are all, now we know that we have Tn action, but TL is a subgroup of Tn. So we can also think of LIs as TL equivariant line bundles, and therefore these LIs, which are the restrictions, are TL equivariant line bundles on this F lambda, which already has a TL action, because this map is TL equivariant inclusion. So there is a TL action on F lambda, and these line bundles are TL equivariant line bundles on F lambda. So therefore, whenever we have equivariant line bundles, we can take the associated bundle. So this was constructed associated to the universal principal bundle. So we can take the associated bundle on F. We have this equivariant Chern classes of this the tautological bundles, but we can consider the TL equivariant Chern classes of these restricted bundles on H TL star F lambda. So they are known as the Chern classes of these land bundles, script Li and Li respectively from 1 to n. So these will play an important role in our description of the cohomology ring, as well as we will come to the K ring soon. So before stating the theorem, we need to fix up some combinatorial notations. So we are also interested in the dual partition. So lambda is a partition. So we can consider the dual partition, the dual Young diagram for lambda. And then, but this definition is true for any partition. So we will define this numbers P lambda check S. So this appear also in Tanisaki's paper. So 1 1 to n. So S varies from 1 to n. P lambda check S. We just take the sum of these numbers from n minus S plus 1 to n. So this sum of them could be 0. I mean, after L, we put them as 0, but for making sense of this definition, we include from n minus S plus 1 to n, where S varies from 1 to n. So we are just adding up the some numbers of this lambda i's. We're starting from the downward onwards up to the last one. So for example, if we take n equal to 8 and we choose this partition 3, 2, 2, 1, then the dual partition is, if you just flip the tableau, you will get 4, 3, 1. So in this case, the number we'll choose L for us here will stand for, we'll be interested in this number of partitions here, 3. So P lambda check S, this number is 0 from 1 to 5. It won't, we won't get any number because they are starting from n minus S plus 1, but there are no terms here from L plus 1 onward. So if the maximum is L, because we have put them as 0, but then P lambda check of 6 will start to be 1 because this is 1, and then 3 plus 1, 4, and then this is 8, 4 and the total number, and it stops there. So this varies between 0 and 8 in this way. So these numbers are going to be important because they appear in the relations in the cohomology ring. And another combinatorial notation we need to fix. So we are just giving some map from 1 to n to 1 to L in this manner. So we'll just define a tuple. So we need to fix this. So before this, so what are this? So U1 up to UN. So they are this is a polynomial ring. BTL is a polynomial ring with, we fix some polynomial ring. So this is isomorphic to H star of BTL. So we need to fix, once we fix that, we're just giving this map from n to L in this manner. So phi lambda, it will be one of the numbers from 1 to L, depending on how we are giving this sequence. So U1, it just repeats, then U1, U2, that occurs exactly lambda r minus lambda r plus 1 times. Because they are decreasing, we can repeat it so many times. The total will be n, because there is a partition of n, so lambda 1 up to lambda l. So we just need to give this, again, this is a notation which is fixed combinatorial, which will help us for the action of TL, because we need to tell how TL acts on Cn. So it will act by these characters. So because if we know phi lambda 1 up to phi lambda n, it will be easy for us, but it is just given by this formula. So now we will state the theorem, this definition of this presentation. This is the cohomology ring with this polynomial ring with coefficients in H star of BTL. So that we have already seen that if this is Z U1 up to UN. So if we take the polynomial ring Y1 generated by Y1 up to Yn, and UI, where UIs are just this Chern classes of the trivial bundles here, the associated to this ETL, they are elements of the base, the cohomology ring. And so they are given by the coordinate projections of the character. So this is standard. So we define this ideal in S, which is given by these elements. So this is a product of Ek yi1 up to yis times h t minus k u phi 1 up to u phi lambda s plus 1 minus d. So exactly this k varies from 0 to d. Ek are the kth elementary symmetric functions, and h d minus k are the complete symmetric functions. So d minus kth complete symmetric function, and this s varies from 1 to n, all possible. And we are just taking some increasing sequence between 1 to n, I1 less than I2 less than Is. And Q is just a notation for P lambda checkers, which we already defined. It just makes it simpler to define, call it Q. And this D is bigger than equal to S plus 1 minus Q. So this is very important for us. D is always bigger than equal to S plus 1 minus Q, and this K varies from 0 to D. So these are the relations. As we can see, they are involving these coefficients here and these polynomials. Then, so the theorem of Abe and Horiguchi is that if you can give the map pi lambda, where you send yj to the first Chern class of the line bundle Lj from 1 to n, then this is a surjective homomorphism. That means it is generated by these Chern classes, and the kernel is precisely the ideal which we just now saw, given by these relations where these varies over the symmetric function and this S varies. So this is the theorem of Abe and Horiguchi. So we will now, our main aim in this talk is to give such a presentation for the TL equivariant K-ring, the topological K-ring of the Springer variety. So we need to give some generators and relations. So firstly, we also need to give some generating the line bundles, as well as define the correct relation. So yeah, so we will now start with the basic definition of equivariant topological K theory. So for us, X is a G space, some space with the action of a compact connected Lie group. And for by G equivariant K group, so we take the free abelian group on the isomorphism classes of G equivariant complex vector bundles on X, and we go by some relations. So the relations are just whenever V is isomorphic to the direct sum of these two vector bundles, we just say that the class of V prime plus V double prime in here is the class of V prime direct sum V double prime. So by equivariant vector bundles, we mean that, so on X, there is a G action. So if V is an equivariant vector bundle, so we define an action on V. So it should be, there is a projection. So it should preserve the G action on the base. So over X, we take the fiber, and then as X goes to say Gx, G dot X. So we need to say that there is a isomorphism, the linear isomorphism phi G from the fiber over X to the fiber over Gx. There is a linear isomorphism given by G, and whenever there is a multiplication G dot G prime, phi of G dot G prime is phi G prime composed with, I think, phi G. So this, it may change, but then it respects the linear isomorphism, preserves this group action, and phi identity is the identity linear isomorphism. So this is how we define equivariant vector bundles, and we give this, take the isomorphism classes and go by this relation. So we also know that there is a ring structure, because tensor product of equivariant vector bundles will again be equivariant, will again admit a G action. So this has a ring structure. So this becomes ring, the topological equivariant K-ring. And in particular, if we just take the trivial vector bundle with trivial G action, that will give the identity, multiplicative identity element. If we choose a point, so what are equivariant vector bundles over a point? So point is G fixed. So that means there is a map from Vx to Vx, the G gives there is an action. So that means Vx becomes a G representation space. So this can be identified with the representation rings, all possible representations of G. This will be the over a point. So, and then whenever we have a map, we can give pullback of vector bundles. So that automatically gets an RG algebra structure from this map to a point. So I will first give the definition of the ring, the presentation, and then we will explain how we prove it. So this is the ring script R, which is the K-theoretic analog of the Abe-Horiguchi's ring. So the coefficients here are, instead of H star BTL, we are taking the representation ring of TL, of the TL which acts on F lambda, and the polynomial ring in n variables, which we call as x1 to xn. So RTL is nothing but the representation ring is the Laurent polynomial ring in exactly L number of variables. So how do we get the Laurent polynomial ring? Corresponding to the one-dimensional representations of the torus coming from the various coordinate projections. And this is isomorphic to the representation ring is all, or they are all be generated because it's a torus. We know that it will be given by the one-dimensional representations will be generated. So this is the Laurent polynomial. And we define an ideal which is very similar to the ideal given by Habe and Horiguchi. So this ideal is generated by the elements again. This -1 to the power d minus k, e k, xi1, xis, and then h d minus k, this the same elements, but where one varies, s varies from 1 to n, and these are some tuples between 1 to n, and this q again denotes this p lambda check s, which we have already defined. This number we have defined, and d is bigger than or equal to s plus 1 minus q. So this is similar, but we will now change the map, because earlier the map mapped it to the Chern class of the line bundle. So now we will send psi lambda as a map from R to the topological TL equivariant topological K-ring of F lambda, which is defined on the generators, on the polynomial ring generators. Xj goes to Lj, the class of Lj in the TL equivariant K-ring of this. So in the TL equivariant K-ring, it is generated by the equivariant vector bundles. So these are equivariant line bundles, TL equivariant line bundles, and the class there for 1 to n. So these we show that they generate. That means if this map is surjective, so these line bundles generate the K-ring, and the kernel is given by the ideal with these relations. So we need to show now this theorem. So the method of the proof of this will give an idea now. So we will recall again some more basic facts which are used for the cohomology ring, the equivariant cohomology ring, as well as for this equivariant K. So we recall again that this Springer variety has an algebraic cellular decomposition with the cells looking like affine spaces, or it is equivalently paved by affine spaces. So there is a filtration with, when you take the successive differences, they are affine spaces. So this was proved by Spaltenstein, and there are exactly n choose lambda cells. These correspond to the fixed points. This cellular decomposition is also TL stable. That was again in Spaltenstein's result, and also the cells are, we can wonder, because the flag variety has a cell decomposition given by the Schubert cells, or the and then how they relate to these cellular decomposition. So in fact, the cells here are intersections with the cells of the full flag variety of the to the Springer variety, and they do arise as intersections. And this can be found in the result can be also found in this notes by Juliana Timochko, and it is also there in Spaltenstein's paper. So we can prove, we first begin with the theorem which can be proved for any T cellular variety. This is a general fact. Whenever there is a paving the affine spaces, we first show in a general fact that the topological K-ring is a free RTL module with rank exactly the number of cells, where M could be the number of cells. It could be any X. There is a X is X1 and we are having X2. XM, we can stop with a fixed point. There are M fixed points, and every time we are taking Xi minus Xi plus 1 is some affine space. So there is such a paving. So there are this is more generally we prove it, but in the particular case of the Springer variety, this will be a free RTL module of rank n choose value. And also we know we call this I lambda, this inclusion in the flag variety, and then this will induce a pullback morphism. This by pullback of vector bundles. The cohomology also it induces, which we call I lambda star. Here we call it I lambda streak following Atiyah-Brooks notation. So this is by pullback of equivariant vector bundle. So we already know that this has an so this is by this has also gets an RTN module structure, because we have this inclusion of RTN inside TN, but that will induce again in the opposite direction, because this is the restriction that any TN representation we can think of it as a TL representation through the inclusion. So we have a map. So the whole map can be seen as RTN module homomorphism. So this pullback map, and this is a map of RTN algebras. This pullback. So again, using this cellular decomposition, which we know is the TL equivalent cellular decomposition, we can show that this, because by the inductive argument, because the cells are coming, there is a cellular decomposition for the flag variety and for the Springer variety, but the cells are intersections. So by an inductive argument, we can show that this map is a surjective homomorphism of RTN algebras by taking induction on the cells on this thing. So now we can also recall the fact about the structure of, so this is one of the Springer varieties, but it is well studied, the full flag variety, and its TN equivariant K-ring is known, studied by many people, MacLeod and Constant and Kumar, they have studied it, and this presentation will come as a result of this study of this, the equivariant K-ring of this full flag variety. This is the AN case. So we can describe it. So the very similar presentation is known for the equivariant cohomology ring. And the same presentation we can give for the equivariant TN equivariant K-ring of the full flag variety. So RTN, the representation ring, we take the polynomial, sorry, this should be X1 up to Xn. And the difference between the elementary symmetric functions, EK X1 up to Xn minus EK T1 up to Tn for 1 less than or equal to K less than or equal to N. So this will be isomorphic, where the map is given by sending Xi to the Li Tn equivariant K-ring, the element of the K-ring of this line bundle. These are the tautological line bundles. And Rtn has this Laurent polynomial ring description, where T1 up to Tn denote the first up to nth projections. Those characters. So it is generated by that. And this can be shown from the descriptions due to McLeod and Constant and Kumar. This follows. So, so therefore, in particular, because of this, we know that these generate this KTN of F as an algebra. These line bundles generate. From the previous theorem, we know that this is surjective. So combining these two, we can show as a corollary that this is generated by the restricted line bundle classes. So in fact, it shows that this TL equivariant carrying of the Springer variety is generated by Li TL for 1 less than or equal to I less than or equal to N as RTL algebra. It will, yeah.
So in the equivariant K string of that variety, we
Yes.
have this relation.
Yes.
Do you have simple geometric reason that we have this relation?
Yes. Yes. Yeah. So this is isomorphic to this kind of a tensor product over RG, where RG can be identified with the while group. So here the while group is Sn. So we have an isomorphism for the Tn equivariant carrying of the flag variety FLN, the F which we call as F, as the tensor product. So this is Tn and this is RG, where G can be identified with this SLN. So the representation ring of RG can be viewed as the invariance under the symmetric group of this. So because of this twisted tensor product, we can show that how this invariants, they map here and invariants map here. So they both get identified because of the twisted tensor product. So we can, first of all, this isomorphism follows because of the Constant, Kumar and the McLeod description. And once we have this, we can form twisted, this from the twisted tensor product. It just means that it is going modulo the relations where how this is sitting inside this, which is EK, the T1 up to Tn minus EK x1. The first one is, the first map is the map which sends xi to the class of Li. The second map is coming because of this getting an RTN algebra structure, because there is a map to the point. So this has a natural RTN algebra structure. The first map is that map, and the second map is a characteristic homomorphism which takes any xi to Li. So because of this twisted tensor product, we can show that these relations hold. But in one place we can forget the Laurent polynomial thing. We can avoid, and we can actually get a polynomial quotient of a.
That's very good to know. I also wanted to know that, but the algebraic reason.
Oh, okay.
Those classes
Okay.
represent the class of vector bundle.
Oh, these.
When K is 1,
Yes.
E1, X1, it's just sum of X, right?
Yes, yes,
That
yes.
corresponds to the sum of line bundle. Oh, it is sum of line bundle.
Yes, yes, yes.
But that is clear. So I think the EK is just taking an exterior power.
Taking exterior power. Yes, yes.
We are
Capex.
taking the exterior power of the trivial bundle. That's why.
Yes, yes, yes. I think we will see it again. Yeah. Oh, yeah. It will come again in the, I think, in the Springer variety situation. How much time do I have? 3 minutes. Oh no. 20. Okay. Okay. Sorry. Okay. So I thought only 3 minutes. Okay. So we have the action. So we recall the action of the symmetric group. So again, we have till now we have shown it is surjective, the map from the flag variety, and we have. So we now need to also give an action of the symmetric group on this KTLF. So for this, we follow almost the same techniques as in Abe Horiguchi's paper, where they give an action of symmetric group on the cohomology, TL equivariant cohomology. So we will begin with giving an SN action on the flag variety, which we know. So there is an action of W in SN. It just takes the flag to the permuted flag. We just permute the subscript, and then we get a full flag again. So this is the way SN acts. So the pullback of the line bundle Li, we have already defined this tautological line bundles, and how there is also an action. So how this action is given on the carrying of the full flag variety. So it just takes this Li, which are the generators, to LWI. So these line bundle maps to the line bundle which is permuted line bundle. So this again in the carrying from the ring description, we can see that W does not act on the coefficient. So WTI is TI and WXI goes to XWI. It's because XI maps to the line bundle. So this is with reference to the presentation. We again recall that the TL fixed points, they are indexed by the right coset representatives, which is n choose lambda of this product of the symmetric group in Sn. There should be a product here. So yeah, this description is again known by the paper. So then we have the restriction map. So now this is standard. This is called as the restriction to the fixed point in the cohomology theory. So we have exactly m fixed points where m denotes as n choose lambda, and this KTL of this fixed point set is the product of RTL, where I goes from 1 to n. There are m to the power m number. So this map we show is injective. This map is injective. This localization is injective. So again, this follows because after tensoring with Q, it's injective by the general K-theoretic equivariant K-theoretic Segal's ring, Segal's results, equivariant K-theory results, classical topology. But this doesn't have any torsion. So this is a free module. So this will be injective. So and then we have this. We can do the same thing for the flag variety. We have this restriction to the fixed point, and here for the Springer variety, and we have a commutative diagram. So this is coming from the restriction I lambda per straight, and this map is given from the fixed point set to this fixed point set. But we know that there is this map. Whenever this TL is included inside TN, we have the projection. So this map will be at the projection whenever this fixed points, whenever W is the coset representative, because they are a subset. The fixed points in this are subset of the fixed points in the full flag variety. So whenever they are in the subset, it will be the projection. Otherwise, it's the zero map. So on the right side. So then we can show that there is an SN action by using this commutative diagram. We can show that there is an SN action. So in such a way that this map is SN equivalent. We already know this SN action, but we can give an SN action by using this restriction to the fixed point and show that this map is SN equivalent. And how this map is given on the restricted line bundles, it acts in a natural way. It is just LWI, okay, TL equivariant class of that. W dot Li TL equivariant classes, the TL equivariant class of LWI, where these are the restricted line bundles on F lambda. So, okay, before now it only remains to justify the presentation, the relations. So, the similar arguments are used right at the beginning by Anisaki and Abe Origuchi, and also for the ordinary Kering, we use similar arguments in my paper with Sankaran. So now we will do everything equivariantly. So we need to give justify the relations. So for that, we have this proposition. So there is a splitting of this by some trivial bundles. There are q number of them. This q occurred, which was dependent on this lambda. Q was our notation P lambda check S. So we can split off q trivial line bundles when we take this direct sum decomposition of Li1 direct sum Lis. So psi is some vector bundle of rank precisely S minus Q. And where D is, but if D is bigger than or equal to S plus 1 minus Q, we can do just modify this little bit. So psi prime, we can absorb some of the trivial pieces here. And there will be some splitting here, epsilon J1 up to epsilon S plus 1 minus D. They are all trivial bundles. The biggest thing is Q maximum. This can be a smaller number. S plus 1 minus D can be less than or equal to Q. So again, we can split off that much. So this will be a trivial equivariant vector bundle of rank D minus 1. So this is important to note the rank of this. So whenever this I1 up to IS vary from 1 to n, we can split like this. So now this P lambda check S, they are not some combinatorial numbers alone. They occur as rank of this. We started with a nilpotent operator, n to the power n minus s. If we take the rank of that matrix is precise. This is in Spaltenstein. This was, I have to mention, I think I should have written, this is theorem in Spaltenstein, that this is rank of n to the power n minus s for 1 less than or equal to s less than or equal to n. And if we can choose this filtration of Cn by just taking the image of n and then image of n square, etc. We know that L lambda 1 is 0 because it is the largest Jordan block. Between that, we have all this. And we also know that because of the definition of the nilpotent, the Springer variety, we can always, for any in the element in the Springer variety, inside Vs, if we fix this full flag, which needs to refine this flag. So we can always show that this UQ will be contained inside Vs. So because that again comes because of this definition of the Springer variety. So by changing n by some conjugate, we can assume that this UQ, the Q dimensional subspace of Cn, is the standard subspace, C to the power Q. So this Q is again the same. So now this is the map which I said is considered in the various arguments earlier. We again use the same technique. So we take the full flag variety and we map it to the S-dimensional subspace. So it goes to the Grassmannian NS, Grassmannian or S-dimensional subspaces inside Cn. So we just map it to that. When we note that what is the image of the Springer variety inside the Grassmannian, this is precisely given by those S-dimensional subspaces of the Grassmannian, because as you have seen, it always contains this. So those S-dimensional subspaces which contain UQ, which contain the CQ, which has been identified with UQ. So that is a Schubert variety in the Grassmannian. So it maps to the Schubert variety in the Grassmannian given by this condition. This is also a smaller Grassmannian, but we just need this definition. So we know that TL commutes with n. So all this inclusion maps F2, the Grassmannian, this maps, because there is a TL action on everything, because by restricting the TN action, so everything is equivariant under TL action. So we take the tautological complex vector bundle of rank S on the Grassmannian. That means a fiber over any element of the Grassmannian is the vector subspace A of Cn, the tautological complex vector bundle. And we know that this is again TL equivariant. It is Tn equivariant, but we just take TL equivariant with respect to this action. So, and what is the restriction of the tautological vector bundle on the Schubert, on this Schubert variety? We know that because it contains that subspace, it will split off. This is a trivial bundle. This will always contain a sub bundle, which is a trivial bundle of the rank Q. And this will be another bundle of rank S minus Q. So we can just pull back. Now this is a trivial bundle, but we have to note that everything is TL equivariant. So the action of TL now is coming because of this phi lambda, which we defined first. We defined the phi lambda from N to L. So that is how the TL action is coming on the fiber. So now we can just pull back this and we get the splitting. And now we use some lambda operations in equivariant K theory there, which are the exterior operations. And this lambda operation will take any x to some lambda I, some power series ring. But whenever we have a vector bundle of some rank, this will be a polynomial because lambda k will be 0 for k bigger than or equal to d. Whenever it's more than the rank, it will be 0. So these are lambda operations. And if we perform this lambda, this satisfies this property that lambda naught is 1. And if you have a line bundle, lambda t is just a polynomial of degree 1, as we have seen. And lambda t of x plus y, this is very important for the relations. It is lambda t of x times lambda t of y. It's multiplicative here. And now we recall that we gave a splitting of this in the proposition. Sorry. Yeah, that, yeah, here. Of the vector bundle. Yeah, sorry. Yeah, here. So because of this splitting, we can now apply the lambda t operation because it splits off so many trivial vector bundles. And when you apply the lambda operation, we get this relations because this is the rank S minus Q. And so it will go to the other side because of this. We can take the lambda t of x plus. So this is lambda t of x is lambda t of x plus y inverse. But then we know that this it's inverse. This inverse of this polynomial will come. But that is how this complete symmetric functions come here. And these will give the elementary symmetric functions we can add. And these will be 0 in the, these will be 0 because this degree d terms, we have to compare the degree d terms. And this was precisely of degree. It was precisely of degree S minus, so degree less, the d minus 1. So degree less. So degree d terms will vanish for that. So therefore we get these relations involving the elementary symmetric functions, polynomials, and the complete symmetric polynomials from here. So we get these relations. So okay, I think we can, so we can just give the map and the relations, why these are the only relations. Again, we have to compare the dimension. This is as a RTL module, this is rank n choose lambda. So we need to give n choose lambda generators here. So which we do again using the cohomology, the equivariant cohomology results. So then this will prove that this is an isomorphism. And we can compare it. This is called as K-theoretic equivariant formality. So this is this was defined by Harada and Landweber. So we can now show that this is K-theoretically equivariantly formal, the Springer varieties. So what is this map? This is just forgetting the TL structure. You take a vector bundle, you forget the TL structure. And the Z to this, we can just give the trivial bundle, the map. And then this is the class of the trivial vector bundle of rank n. So now we therefore define a map from this tensor product to this. And we can show that this is an isomorphism precisely because this is already, because it has a cell decomposition. This is with n choose lambda cells. This is free Z module of rank n choose lambda. And this is free RTL module of rank n choose lambda. So this tensor product left hand side will be free Z module of n choose lambda. This is surjective because we have shown that this LIs generate, the LIs generate by the results I gave for K theory. We know that LIs generate here. So this becomes an isomorphism. So we can also recover the presentation. If we just know that Li generate, we can also recover the presentation by putting these UIs as one. So yeah, this was proved, the presentation was proved by other methods in my paper with Shankar. Yeah, thank you. Thanks. Yes. Yes.
Maybe I missed something, but
Yes.
what do you mean by weekly equivariant?
Okay. Okay. So the definition of weakly equivariantly formal is that this map is an isomorphism. This map where the first map is the forgetful map, and the second map is the rank, the n goes to the trivial vector bundle of that rank. Then we can always define this map from this tensor product to this. This is how they have defined weakly equivariantly formal. So in particular, we show that the Springer varieties are k-theoretically weakly equivariantly formal because of this.
So it means we can recover the ordinary one.
Yes. Yes, we can recover from that presentation. We can recover. So for cohomology also, it's true that we can recover Tanisaki by just putting UIs as 0. We will get the Tanisaki in the earlier the result of Habe Horiguchi. If we just substitute UIs as 0, we'll get. I wanted to say that, but I missed. If we just put UI 0, we exactly get this ED yi1 up to ys. So there, that is the Tanisaki's presentation. So here also we can get the recover our presentation from there. So this is in an archive. This paper is on archive. My paper is on.
Now, what do you mean by equivariant formal?
So that.
Not weekly, not weekly.
Okay.
That's equivariant formal for theory.
Okay. So yeah, I don't know very well about that. I have not. I have only seen this definition by these works of Harada and. Sorry.
Are there any GKM have restriction?
Yes. This is the but not the curves are not known, but we have the restriction to the fixed points. That's what we use here. We very much use the restriction, the localization. Okay, yeah, we don't know the graph. The curves in F lambda, the one-dimensional, the P1s in F lambda, whether we know that. I'm sorry, I'm going to talk. We use a localization, but we don't know the. Sorry, I think I missed that. We use a restriction to the fixed point. That is how we prove this. But whether we know, here we know the GKM, here we have GKM. But here, whether the curves are coming from, which are the curves here which join the fixed point? I don't know whether it is known. Is it known?
Points are finite.
Yes. Fixed points are finite.
There are invariant PL invariant curves are infinitely many.
No, I'm not saying that they are infinitely many, but they have to be the curves in F as well. The TL invariant curves in F lambda have to be TL invariant curves in F because they are fixed points of F as well. But which are the TL invariant curves in F lambda which lie inside F lambda?
But if those curves are finite,
Yes.
GKM.
Yeah, they are finite. They are finite because every TL equivariant curve must be a TL equivariant curve here. But there we know the TN equivariant curves, but whether they are the same as the TL equivariant curves because it's again P1 which joins those two fixed points. I don't know whether they are exactly the same and yeah, then there will be just finitely many and therefore it is GKM. But I have not seen.
In finitely many cases, then maybe we can get the
Hmm,
together. Even in infinitely many, there is an tier breading exact sequence. So we can write this equivalent homology as almost the equivalent homology of the one state.
Okay.
Equivalent case of the
You
one.
can keep it on one skin also. Okay, okay, okay. If we know that everything is coming from the one skeleton, that the curves, the term, yeah, yeah. So the description of the curves, I have not seen it before, like whether they are the same as the Schubert curves, which are joining the fixed point.
I have a question.
Yes.
So, does we this notion of current formality?
Yes.
Why exactly?
Okay. Okay.
Do we have
Mhm.
Chang
Chang,
Gilbert's?
Chang scale.
In the case of is an tier bread.
Ah,
It's called tier bread.
starting.
Here.
Yeah.
Equivalent homology is there.
Okay.
Mhm.
So, the purpose is the thing is